Hi, my name's Joe. This is our paper, Distilling Robustness into Natural Language Inference Models with Domain Targeted Augmentation. This paper is by myself and by Marek Ray. So our idea is, can we improve robustness on altitude distribution NLI datasets by generating data for target domains in these datasets with an LLM? So first we generate a premise statement. You can see on the right hand side we ask the LLM to generate an example extract from a popular magazine article. And that's one of the domains in the MNLI dataset, which is in this case our altitude distribution data. We generate this premise statement and then we generate another statement, a hypothesis statement conditioned on this premise. And we try generating hypotheses that are entailment, neutral and contradiction. The problem is though that the labeling just isn't consistent. You can see in this case, so premise, if you're considering prescription drugs to treat a medical condition, talk to a doctor first, and hypothesis then, prescription drugs can have serious side effects. Well, this hypothesis isn't really truly implied by the premise, kind of showing you some of this inconsistency in the labeling. In the table on the bottom, you can see performance for baseline model and then model where we also train with additional labeled altitude distribution data, and actually robustness decreases, which you can see the figures in the blue box compared to the numbers above. So instead of trying to label this data better, our idea is, can we use this data as unlabeled data and use it with knowledge distillation? So we find the best performance in knowledge distillation is when we first fine-tune a teacher and student model on the in-distribution data. That's our SNLI training data. We then perform distillation to encourage the student to behave more like the teacher model. But for labeled examples, so that's our SNLI training data, we only perform distillation when either the teacher model predicts the correct class or when the teacher is more correct than the student model. Because we don't want to perform distillation when the teacher's both wrong and more wrong than the student. Top right, you can see distillation loss. We consider the sum of the squared errors between the probability distributions in the student and the teacher models, summing across the classes C and each instance in the dataset. But we could also use an ensemble of teacher models, in which case we take the mean probability distributions from the different teacher models represented by Qi in the equation. So using this distillation setup with our domain targeted augmentation, we see substantial improvements on the MNLI altitude distribution datasets. So both for the domains we target, which are the domains in the MNLI matched validation set, but also in the MNLI mismatched validation set, which is entirely different domains that we haven't targeted or generated any unlabeled data for. You can see these results in the blue box comparing standard distillation to our domain targeted augmentation approach. You see quite a small improvement for SNLI hard. It is a significant improvement, but it's very small. So the question is, can we increase this benefit on the SNLI hard while maintaining performance benefits on the MNLI matched and mismatched altitude distribution datasets? We achieve this by introducing distilled minority upsampling, DMU. This works by, when we first fine-tune the student model, we then predict, or we test that student model on the training data it was trained on. And we see any training instances that are misclassified by this model, we call them minority examples. It's essentially in-domain examples that are challenging because they have a different distribution from the rest of the training examples. We then perform additional distillation by upsampling these minority examples during the distillation phase. So we can see the results of this DMU method, where we now see substantial improvements on SNLI hard. So it's over almost 6 percentage points higher than the knowledge distillation baseline, although there's some trade-off with performance on the MNLI altitude distribution datasets. Thankfully though, our methods prove to be highly complementary, and we see significant improvements across SNI hard, MLI matched, and MLI mismatched. There's also significant improvement in domain, but it's very small, and that's not the focus of our work. So the question is, can we better identify these minority examples? And an idea is, instead of just using one student model, we also consider 7 other models with the same architecture as the student model. And if any of these fine-tuned models misclassify any of the examples in the training data, then we say it's a minority example. So we're using an ensemble to help better identify the minority examples. If we do this, we see a further improvement in robustness on the SNI hard datasets. You could also use an ensemble of teacher models as well, although we find if we also do this in this setting, we find kind of a very small additional improvement, which you can see on DMU full on the bottom table. So inspired by this, we kind of want to look at, does using an ensemble of teacher models actually help, both in distribution and out distribution? Previous work had found that it does help in distribution on your in-domain test sets. We also find that it helps out distribution. In fact, if you use an ensemble of teacher models, you see greater improvements in robustness compared to the improvements in distribution. In this case, we use the same architecture for our student and teacher models. So we distill an ensemble of models into the same architecture but into a single model. The improvements are relatively small because we see small improvements from distillation in this setting. See results from BERT and then from DBERTA, where we also see significant improvements. We then look at, is our domain targeted augmentation method also effective in this setting, where we distill from an ensemble into a single model of the same architecture? And we find, yes, it is. So significant improvements for both MLI validation sets for both BERT and for DBERTA. That's compared to standard distillation baseline. We then compare this method to previous work where you train on SNLI and you then test robustness on MNLI. What we found is that distilling from this ensemble using our domain targeted augmentation actually outperforms all previous robustness work in this setting, some of which also uses ensembles or kind of different pipelines and models. So our method proves to be highly effective in this setting. And finally, we test robustness across a whole bunch of different settings. We talked about training on SNLI, testing on MNLI. We also train on MNLI, test on hands, test on SNLI, test on SNLI hard. We try 9 different configurations of student and teacher models, and in each case we perform 10 experiments and do statistical testing over each of those 10 different results. So yeah, there's a lot of experimentation. Thank you so much. Thanks for listening, and I hope you like the paper. Thank you.